geologist. So I've already learned a lot from this meeting and looking forward to learning more over the next few days. This is some work that I did during my PhD at the University of New Mexico about 3 years ago now. So I won't dwell on this. The last few talks have covered this very nicely, but there's clear evidence for carbon on the surface of Mercury. We have data from Patrick Keselowski's work showing this higher abundance of carbon in the northern hemisphere in these low reflectance plains. And this might actually be the graph that Rachel was just referring to. So Scott Murphy and coworkers also showed that you can take an average northern volcanic plain spectrum, which is the largest volcanic field on the surface of Mercury, and by adding 7 weight % graphite, you can darken that spectrum to about the same as this low reflectance material. So Patrick went on and did some more work and showed that the only element consistent with both the neutron measurements and the visible to near IR spectra of the low reflectance material is carbon. And he showed about 1 to 3 weight % greater carbon in the low reflectance materials than the surrounding regions. So from this work, he inferred that carbon is the primary darkening agent on Mercury, and that the LRM is actually sampling carbon-bearing deposits within the planet's crust. And then more recently, we just heard from Rachel that the LRM seems to be excavated from depth. It may be enriched with as much as 4 weight % carbon over the local mean, and the carbon present is likely endogenic rather than exogenic. So there were a ton of instruments that were on the Messenger spacecraft. The 2 that are important for the work I'm about to show you is the GRS, which measures the suite of elements shown here, and also the XRS, which gives us our major elements that we're working with. So based on this data, we learned some pretty interesting things about Mercury. The surface was shown to have high sulfur abundances, so around 4 weight % sulfur, as well as low FeO abundances, so about 2 weight % iron. So with this data, there's been a lot of calculations about the oxygen fugacity of the planet, and it's been shown to be very reduced, so somewhere between about 3 to 7 log units below the iron Woodside buffer, making Mercury the most reduced of the terrestrial planets. So what we wanted to do is look at this end member and experimentally determine the density and the compressibility of Mercurian melt compositions. And we did this using a technique called sink float experiments, which I'll discuss in a minute. And we wanted to assess the eruptibility of these melts onto the surface of the planet. So the silicate composition that we used was the northern volcanic plains composition. So these are smooth plains that cover about 12% of the northern hemisphere of the planet. There's no evidence of an impact basin nearby, so they are believed to be volcanic. And down here you can just see, the northern volcanic plains superimposed on North America. So this is a huge region of lava. It's the most likely example of lava that can be compositionally assessed from orbit, and therefore the best candidate to experimentally study the Mercurian interior. So this is just to show you the compositions that we use. The composition of the northern volcanic plains is shown on the left, and the composition of our starting material that we use is shown on the right. So the first thing that you'll notice is we removed sulfur and alkalis from our starting material. These would both decrease the density of our melt, and we wanted to see the maximum density of melt on the planet to assess the eruptibility of these onto the surface. And then also we have about 5% iron, which at this point is pretty unrealistic for Mercurian melt, but it gives us that end member of density. So again, to assess how dense can a melt be and still get to the surface of the planet. So we did sink flow experiments. These are experiments run in a lab. We used the density markers for these experiments were for 100, and these are used to monitor the density of the melt throughout the experiment. So this is a known technique in experimental metrology. It's used been used a lot in the past. This is just an example of run products. So you see this is a molybdenum capsule. This is actually a lunar composition that is shown here from my master's, but when you have the spheres at the bottom at the end of the experiment, it's a sink, so your spheres were more dense than your melt. We also can have floats where they remain at the top, and we can have neutral buoyancies where one has stayed at the bottom and one has stayed at the top. All of our experiments were run in the multi-anvil at the University of New Mexico, and we ran experiments between 2.5 to 6 GPa. So you can see a cross-section of the experimental assembly here. We start by placing a sphere at the top and the bottom of the capsule. We fill the capsule up with our starting material, and it's then placed inside a ceramic octahedron for the run. Once we have the ceramic octahedron constructed and closed, we place this octahedron in between 8 tungsten carbide tubes. And of course, throughout this entire process, it's critical to make sure you always are aware of where the top of your capsule is. So we like to draw these huge arrows and make sure that the top of our capsule is always pointing up during an experiment. We pressurize at about 1 oil bar per minute, and then we ramp up the temperature fairly quickly. We hold at these target conditions for just about 30 seconds before shutting off the power and quenching the assembly and then slowly decompressing. So these are our possible results that we can get. We get a sink, suggesting that the spheres are more dense than the melt. We can get a float, suggesting that your spheres are less dense than the melt. Or we can get a neutral buoyancy, suggesting that your spheres have the equivalent density of the melt that you're looking at. And since we know the density of the spheres that we're using and the equations of phase that accompany those, we can then bracket the density of the melts that we're looking at. So here are our results. So you have density on your Y and we have pressure on the X. Just to keep in mind, the core mantle boundary on Mercury is probably around 4 dPa, maybe as deep as 7 dPa, but we have a very shallow mantle on the planet. So we use a calculated 1-bar density and the brackets from our sink flow experiments to determine the density of this melt. But we wanted to get a range of densities, and here we only looked at one composition with high iron. So what we did was, again, looking at density versus pressure, we calculated a 1-bar density for an iron-free version of this melt and offset our line. And then we also calculated equation of states for the iron-free Komatier and the iron-free KLB1, which are terrestrial samples. So with this, we get this kind of red region that you see, and we're using this to indicate the range of melt densities on Mercury. So from here, again, looking at the same density versus pressure plot, we want to compare this range of melt density to possible minerals that are going to be forming. So when we see a crossover where a mineral becomes less dense than this magma ocean melt, that mineral is thought to then float in the melt. So you can see here, all of our typical minerals that we think of, again, we use magnesium, end members, so your andesite, your forsterite, they are all more dense than this melt. The only one that has a density crossover is this AN50. However, this crossover occurs at pressures where AN50 would not be stable, so we don't think that crossover is going to influence anything. But if you look at this graphite curve, you can see graphite is always less dense than our magma ocean. So if graphite floats to the surface of Mercury, we would then expect the surface to be dark, which we know from the last few talks that it is. So this is just showing you a comparison with Mercury to the moon, and as Rachel stated, the darkness of Mercury is comparable to the Maria of the moon. So we're assuming that graphite is in fact the darkening agent on Mercury. So how does this play into the thermal and magmatic evolution of the planet? I'll step you through a schematic that we think is plausible from a geochemical standpoint. So we start with a Mercurian magma ocean. We have highly reducing conditions in the nebula, which results in a large ion-bearing core. This yellow line here is a possible iron sulfide layer. It's not actually necessary in newer models, but back when this work was conducted, it was needed for geophysical constraints. So with this low oxygen fugacity, you're actually able to put a lot more silicon into your core. There's been estimates of upwards of 15% silicon in the core of Mercury. And the more silicon that you put into a core, the less carbon you're actually going to be able to put in there. So because of this, we end up with increased amounts of sulfur as well as increased amounts of carbon in the mantle portion of the planet. And under highly reducing scenarios, graphite saturation occurs quickly. So we expect this graphite to float to the surface of the planet. We have continued crystallization and volcanism, which ends up resurfacing. And based on our density calculations, you can erupt from as deep as the core mantle boundary on the planet, which Mercury is so far the only planet that can be said for. So we end up burying this graphite flotation crust. So you can see here it's depicted as a thin homogeneous layer. That may or may not be the case, but for the schematic, that's how we have it. So we end up burying this graphite flotation layer with the increased secondary volcanism. And then we get a ton of impacts to the surface. So we get impact gardening, which mixes this graphite layer with the surface materials, giving it an overall darkened view. And then we also get exposure, which Raj, I think this lends to your question. We also get exposure of the remnants of this graphite layer in craters. So the fact that the majority of the LRM is being found to be excavating material from depth within craters, it is consistent with this hypothesis that we had put forward. We also end up with a chemically diverse surface of the planet. These are just a few geochemical diagrams for those interested from a paper we published in 2017. So this does have some implications. So in our 2015 paper, we calculated the thickness of a graphite flotation crust as a function of the bulk silicate carbon content. I will say these calculations, which there's a series of about 7 or 8 of them to get you here in our paper, they do assume that you're producing a homogeneous layer of graphite around the entirety of the planet, which again may or may not actually be the case. But here we can see with as little as about 5 ppm carbon in the bulk silicate portion of the planet, we can produce a crust that's about 2.5 meters thick. So we don't need an excessive amount of carbon to be able to make this graphite flotation crust and see it with the messenger data. So with that, I already see some things in the chat window, but I can also take any other questions.
Okay, thank you so much. Great. Well, let's start with the questions in the chat window.
All right, so Raj asked, what is the estimated density difference between the northern volcanic plains basalts that you used and the Mercurian mantle composition? Magma ocean composition should differ from the basalts that erupted. Graphite will likely be less dense than the magma ocean composition as well, but I am wondering why a magma ocean composition was not used in your sink slope. So I guess the short answer is we didn't have that data. So this work was started in 2012 with the very initial compositions that were coming back. So Larry Nittler's 2011 paper, and I think that the results that are published here was about our 3rd composition because the results coming back from the messenger mission kept changing, but that is why we removed all of the iron and did the offset with the 1 bar density, and then also looked at iron-free terrestrial compositions to try to, we knew we were looking at something that was too dense to look at. So we wanted to look at that large range of compositions. Rachel Klima said the northern volcanic plains basalts are probably among the most iron-rich and dense of anything we found as well. Yes, I agree.
Great. Okay. All right. So I don't see any other questions coming in. Are there any from the telephone line or anybody in Boulder? No? Question here. Okay.
I have a question. So what is the relationship between this graphite layer and, let's say, the volatiles have been associated with the hollows we see on Mercury? Are we talking about the same thing?
So there are some suggestions that part of what is escaping to make the hollows is a carbon-rich material possibly associated with the graphite flotation crust. There's also been chlorine implemented for the volatiles that are escaping there. So, and I'm guessing Rachel has a better answer and is typing that in right now.
Yeah, I was going to type it, but I could talk it if you prefer.
Yep.
Talk it.
Yeah, we find the hollows in association with the LRM almost all the time. So there's a type of hollows that are more associated with pyroclastics, but they're very frequently developing in the low reflectance material. So there's some kind of association, whether it's the graphite is being, changing phases, then we're losing it. And what's left in the hollows that's very bright is just the silicate rock without the carbon. We don't know whether there's sulfides that are also associated with and entrained in the carbon in this primitive crust that are then left to form the sulfides. That's basically the link between those. We see it geologically, but we don't know what the chemical implications are yet.
Then let me ask just a quick follow-up on that, is that would you expect sort of a buoyant magma ocean byproduct to be volatile rich?
A buoyant magma ocean byproduct.
It's essentially your graphite layer, if it's associated with the hollow, should have lots of volatiles with it, right?
Right, yeah, I mean, I think that was one of the main surprising results that came back from Messenger in general is how volatile rich the planet is. So they, they've measured over 6 weight percent sodium Na2O abundances in that northern volcanic plain lava field. So yes, in general, it is very volatile rich.
I have a question, if you can.
Yeah.
So your center graph is showing there down at the bottom the relationship between the amount of carbon in the original composition carbon content of the bulk mercury and the thickness of the graphite flotation crust.
Mm-hmm.
So correct me if I'm wrong, but you could use that to make an estimate of the carbon content of all your initial material that made up the planet if you knew the thickness of the crust very well. Is that
Rachel, did you hear that? Did you hear that, Rachel? So yeah, that's actually something.
Yeah, I did.
That's actually something that we have been very adamantly working on. Is trying, so Rachel and I are actually collaborating with a bunch of other folks, and, that's one of the huge questions for us is how thick is this layer and how does that thickness vary over the surface that we can see.
right?
But,
That would be a great number to know.
yes,
Fun.
yeah, it would be great to know.
It's going to have very, very large error bars, though, because a lot has happened over the last 4.5 billion years.
These landers.
Yes, I agree. A lander to Mercury. Perfect.
Okay, great. Do we have any other questions or discussions?
I have something. This is Amanda. Kind of in general, for the Mercury topic that we've covered now, I'm wondering what the speakers and anybody else wants to say about what are the open questions and things that we can be working on or thinking about for that could be addressed in another workshop.
Yeah, so I think, what Mark just brought up is kind of one of the most important questions for us is how thick is the layer that they're finding, this LRM material exposed at the craters, because then we can, start placing better constraints on carbon content, and then also kind of looking into, all of our models, because it's the easiest way to do it is modeling a homogeneous thickness layer surrounding the entirety of the planet, which is an ideal situation. So if that is the case or not, the thickness of that layer and then inferred carbon contents based on that thickness, I think, are critical to moving this carbon story forward for Mercury.
And Diane Wooden has entered in a question as well, which I think might be trying to address Amanda's point. Another question.
Graphite survive as floaters in the interior of Mercury.
Or was that a question for Kathleen?
Right.
I think it's asking, is there remnant graphite floating around in Mercury's interior? If that's the question, theoretically no, because it's just so buoyant. For graphite to be a separate phase, did it have to be a specific size? Size-wise, I'm not really sure. Carbon saturation happens really quick when we're at these, iron wustite -3. And So any graphite that is present there in the magma ocean, and again, we're at these really low pressures because we have such a thin mantle. So we are, expecting graphite over, say, diamond. But I personally envision it all floating and taking some part in this layer at the top of the planet or surface of the planet.
I think we have a very, this needs to be probed with geophysics. It needs to be probed with what other phases, if there's anything else that would be associated with it. How quickly in your convecting early magma ocean can you actually accumulate this? Are you going to just rip it all back down into the planet, until you reach a certain threshold? So now are you, is it entrained in a quench lid that starts to build up? So you've got, do you have a solid graphite layer ever? Or, I think there's a lot. We're at a very primitive stage of understanding this. And, I think we've got kind of like physical tests that need to be done and talked about, and chemical tests and things like this about, the size of the graphite that makes sense there, even initially. And then we've got it all, under bombardment flux in the early solar system. So what would we be looking for at the surface as far as the nature of it? And is it distributed like little inclusions throughout silicates, or is it large chunks? Because that makes a big difference in what we expect to see in the reflected spectra and probably in the emission spectra too. It's, I think part of why Kathleen and I wanted to give a talk here is because we're like, what? This is mean. Carbon people, help us. Because it's really it's not something we expected.
Okay, great.
I've got one more question, and sorry if this is naive, I haven't been totally following Bepi Colombo and the Mercury stuff, but how can Bepi Colombo help us answer some of these things? Follow-on questions.
So the MERDIS instrument will be, give us the mid-IR detections, which would be really, really helpful.
Yeah,
and,
but I think Alessandro was showing us that a lot of the graphite stuff there is spectrally bland.
Yeah,
right?
well, yeah. And then they've got gamma ray instrument as well.
Gamma ray will help, okay.
And they should get a better view of the southern hemisphere. So that would be useful for them to test whether they see enhancements over these big terrains.
So more coverage, okay, good.
Yeah, so the Messenger spacecraft had a highly elliptical orbit, so we have really good high-resolution data in the northern hemisphere, and then the southern hemisphere just has a very large footprint. It's kind of like smeared across. But Bepi Colombo is planning on taking a more circular orbit, and they'll be able to better define the southern hemisphere, which will definitely provide more information on this for us.
Okay, well, this is a great discussion. Now, Amanda has another question.
This is not Mercury related, so this is for the more general discussion, if we're in that.
Sure, let's do it.
Are we in that, Yvonne? Okay. And
Yeah.
Yvonne is leading discussion. And I wanted to ask this now because after lunch, we're getting into Mars and then asteroids, and I was wondering what people are thinking about the moon, and where's the carbon and why?
Where's the fly?
Carbon in the moon.
What carbon would you expect?
I don't know.
For comparison?
That was for comparing with Mercury, but all the carbon on Mercury comes from the interior, I guess, and so the moon is different that way. But even, I mean, in the samples, we have very little. Would we expect to see more brought in from impactors? Would we expect?
Wait, is the question perhaps whatever was delivered that had carbon in it, did that get destroyed by space weathering, solar wind interaction,
Well,
that kind of thing?
Well, about 2% of the lunar regolith is probably implanted, and the signature of that material is most consistent with carbonaceous chondrites. So that's probably from micrometeorite impacts and the rest, which are dominated by carbonaceous chondrite stuff.
So what do you mean 2%?
2% weight percent. That's what.
Has been modeled as carbonaceous chondrite stuff?
Yeah, I'm not an expert, but that's what the people that study it claim. They say I think it varies between about 1% to 4%.
Like, is that what Carly would say?
Carly Peters?
Yeah.
I don't know what Carly would say. I would assume Carly would say that.
Okay.
So.
Spectrally, it
I mean,
probably doesn't have a, like, you're not seeing the spectral signature.
Right.
Yeah, you're not going to
So
see
how do you
More
know?
a modeling problem.
Yeah.
Right.
I think what they've done is they've looked at element abundances added to the lunar regolith, and they've been able to deduce that about 2% has been added. But, you know, if you had a micrometeorite coming in at high velocity, hits into a zap, then I think it's trickier to look for like a remnant micrometeorite. But everything I've seen in the literature suggests around 2%. I think the lunar source book says that too. So, I think I'd have to go look at the lunar source book, but I think that's the standard number. So.
Okay, and we have a couple of comments related to this. Yeah, Tom Orlando said what I was thinking. There is surficial carbon, and it is processed by solar wind. But then he adds that methane can be formed and trapped at the poles. And then from LPI, there's plenty of carbon in the lunar interior. CO, for example, is one of the main volatiles erupted with volcanic rocks. The abundances of vented carbon have been calculated before. Also, material is delivered from the solar wind and the carbonaceous meteoritic component of the regolith.
Right. Okay. Good. I think that's, I mean, in my mind anyway, a little piece of the puzzle that would be good to maybe hear about next time.
I think too, there's a lot of work out of the Brown group that has looked at the carbon abundances in the interior and them aiding in the eruption of the volcanic gases. So like Diane Wetzel looked at some of that as well as her advisors that she was working with there.
Okay, Diane, Diane Wooden says L-cross saw carbon in volatiles, C2H4, C3HO3, C2H2CO, which took a sideline to H2O detection, but were much more abundant than could have been directly delivered by comets. Okay, good, you're right. Those did get kind of overshadowed by the H2O. Sorry. It is much higher in abundance that could have been directly delivered by comet.
Great.
Okay.
All right. Well, that's certainly the right kind of question to be asking as we're trying to tie these different things together. I mean, one of the issues that I feel when I've moved into the solar system is that we have such distinct groups, people working on this type of planet or these moons or this, this issue, and the crossover isn't knitted together for me as well as I would like. And so I think that's going to be part of the struggle that we're going to have here with this carbon workshop too, if we don't push ourselves beyond that point. So I think Amanda's question was exactly the right one to start thinking about. So think about the other bodies that these things are related to, and then how can we come up with the tall tent poles that we really need to be addressing.
But also considering lunar formation and the story of carbon in the solar system from as it relates to interstellar medium and everything, maybe we would expect it to be very different anyway.
Yeah.
By these other bodies.
Right, maybe so. So we've got input here from JSC, McCubbin et al. 2015, Magmatic volatiles in the lunar mantle, crust, and regolith, abundances, distributions, processes, and reservoirs, includes a review with carbon included. Right.
Okay, good.
reminded of that. And then another one, Needham and Kring, EPSL 2017, reported 0.2 to 2 times 10 to the 19th grams of CO vented with lunar mare eruption. Yeah. Right. So part of this workshop was to try to put together where does the carbon show up today, how does it look, what are we learning from all the observations that we're seeing. So I think it's really good to start here with Mercury and the Moon and looking at that, and then we're going to tie together, hopefully, that with what we find on these other bodies. Does anyone else have any thoughts or comments or overarching questions that you can think of that we can discuss as a group?
Yeah, I have a question. This is Maria. I really like the carbon, what is it called? The carbon continuum that you brought up earlier today, Amanda and Faith. Where does what we heard today about Mercury and the graphite add to or fit in with that part of the continuum?
I think the graphite story on Mercury is consistent with that whole idea, because we had to expect carbon in the inner solar system to be very processed. And especially if it sounds like it's especially processed because it's from the interior, you know, and under pressure and stuff like that. But I think it definitely hangs together.
Where everything fell on that slide.
Yeah. Yeah, I think so.
Okay.
I feel like people used to talk about graphite or graphitized carbon on Mercury. Somebody remind me, because I feel like it was in the polar regions and people were talking about it being brought in by impactors and surviving there. Maybe not as completely graphitized. Does anybody remember this? What was this? I'm going to have to look it up. But that would have been a different source. Is that still a thing on Mercury?
How many good sources of completely graphitized carbon? Also, I guess it depends what you mean by graphite. But
To compare to in the lab? Or
so like what is your outside of Mercury, what is your source of graphite? I mean, carbonation chondrites don't really have pure graphite in them.
oh, right. So it'd have to get processed on the surface or in the body.
Right. I mean, it depends, yeah, so it just depends what physically this actually is. If it's like actual sheets of graphite.
Right.
Versus,
At least something I mean, I think of it as, you know, a spectrum, right?
Right.
So graphitized,
right.
at least.
Okay, we've got a bit of a conversation going on in the chat room here, and it started with Diane Wooden asking, since we think the Moon came from the Earth's mantle, wouldn't we expect a difference in composition between the Moon and Mercury? And a couple people have responded there. I know I saw Bill Botke said the jury's still out on whether the Moon came from the Earth's mantle. Lots going on with giant impact and moon formation models. And from JSC, says it looks like Apollo-era literature gives carbon abundance for lunar finds of about 155 parts per million. I don't know where to stop as I'm reading this. This is kind of an interesting phenomena. I don't think we've ever had a group discussion like this in quite this way. So you guys just, somebody pick up on whatever thread here you want to talk about. But Rachel's got a couple of points. Rachel, you're online, aren't you?
Rachel, you talk about dark material and permanently shadowed regions on Mercury. Is that different from the LRM dark stuff?
So Rachel had to drop off, so she's going to type her response back. She says, yes, this is something different.
Let me rather than typing, because it takes too long, let me just maybe comment on Diane's comment here, in that I think rather than getting, what she's basically asking is, should we expect differences between Mercury and the Moon because the Moon was formed by a giant impact? And I would just say this, something we haven't touched on Mercury yet, is there's still a big debate in the community about, is Mercury made of the planetesimals that formed in that zone, or, well, I mean, certainly Mercury was formed by that, but also did Mercury experience a giant impact itself? And some people have suggested Mercury was a byproduct, or was part of a hit-and-run collision, which gave it this composition. I don't know what, I don't know if there's consensus that's been reached on that. Some people love a hit and run collision for Mercury. Other people say, no, it could just be made of stuff that was made there and it's just very reduced naturally because that's the way the disk was. But I think that bears on this conversation. So, I don't know if there's a good answer for Diane. It's just that there's a lot going on with Mercury.
Okay, that's a really good point, Bill, and I think something a next workshop definitely should include. Diane's bringing up all kinds of great questions, and she's got one for Dale, and since he's right here, I'm going to let him address it. She says, I wish Dale could comment. Outer icy bodies are dark, and amorphous carbon is used to model the low albedo, so I'm not sure I understand how this fits into the carbon continuum.
I don't think we do either, but just to note that the use of amorphous carbon in modeling is just a matter of convenience to do what, as you note, is to adjust the albedo, since we have not only the spectral information, namely color normally, and the albedo, that have to somehow make the models internally consistent, and amorphous carbon is simply a convenient material that doesn't itself introduce spectral features, but just an albedo level that we can adjust. So it would be great if we can determine that amorphous carbon is actually a relevant material other than just a computational convenience. And maybe what's being discussed here today will elevate it to that status. It's certainly worth considering, and I'm glad you raised that point, Diane.
Okay. Well, going back to that carbon continuum, I'm just wondering how other people are feeling, and Dale, you too, about how we can use that to explain what we're seeing across the solar system. Is that going to be the kind of construct that helps us fit all these pieces, puzzle pieces, into place?
Maybe.
Okay, maybe.
Good to think about.
Yeah, it's intriguing. I like the concept. Let's see. Rachel, did we get your stuff? There's a whole bunch of stuff by Rachel that's already scrolled up. I don't think anybody read it out. Amanda, would you like to read those? I'm trying to save my voice.
Okay, so I think some of it, was in response to my question about dark material in the polar regions on Mercury, and she says that there's definitely dark materials associated with permanently shadowed regions. And she says dark in some places, bright in others, but in both cases distinct from the normal regolith, so maybe an organic lag. So,
okay.
I think the main point she was making is that, yes, although we do see dark material in those polar regions that is likely carbonaceous in nature, it is distinct from the lower reflectance material.
is distinct, so. But is it true that a graphite crust that floated up, okay, so I think the LRM was the graphite crust that exposed at craters, and maybe it wasn't necessarily exposed at the polar regions then.
Right, I believe the carbon at the polar regions and the polar volatiles in general are thought to be cometary in nature.
Okay, and Rachel has given us a link with some pictures. Can we go to that? Right, got some messenger pictures. Oh, okay, so she says she's got dual telecons going on at once, so that's why we can't have her verbally. Let's see, she's just saying that the polar dark material is likely carbonaceous, but different from the LRM, which I think we've already mentioned. Okay, thanks. All right, do people feel like we have, finished this conversation? Lunch? So I'm hearing lunch. We have some from JSC. We've got regarding the carbon continuum and how to utilize it. In meteoritics, carbon crystalline ordering is recognized as a means of measuring thermal history of the carbon, and ergo the parent bodies. Carbon structure has been proposed as a means of classifying carbonaceous chondrites and has been used to identify small changes in metamorphic grade of individual meteorites. Right, thank you. So, when we have a follow-up workshop, how should the study of meteorites factor into the workshop? Any ideas on what you would like to see or hear or investigate?
Well, yeah, I know we're going to hear about meteorites later in this workshop. So we might, I think it's today, right?
Right.
Yeah.
Okay, so let's wait till after we do that.
Yeah.
Okay. Diane can recommend Alexander et al. 2017, The Nature, Origin, and Modification of Insoluble Organic Matter in Chondrites, the major source of Earth's CNN. Aromatic moieties are 1 to 3 rings in the IOM. Very interesting. Yeah, I want to look at that. Great. Diane, why don't you just come over here and be in our conference room? It would be really nice to have you here. You're just in the other building. Oh, driving early is difficult. Okay, well, we hope to see you later. Oh, right. She's over the hill. That's right. I mean, not literally. Okay. Okay, so she's just mentioning that that is those numbers are pretty small compared to graphite. The 1 to 3 rings in the IOM.
Relevant.
Sorry, what?
It's relevant.
It is relevant, yeah, very relevant.
Okay.
Okay.
But for
Amanda?
the next workshop, though, I feel like we should hear about lunar origin and get back to that and how that might fit in with the
I do too.
carbon.
In fact, I wrote that down as well. I think that's an excellent question, and you know, it really it speaks to a lot of these other questions as well. So I think we have got to focus on lunar origin here. But also, I'm really curious about the space weathering aspect of what's happening at the surface, and the work that Tom Orlando and Bill Farrell and others are doing in that regard have really intrigued me, because I know that that's happening, you know, on the other airless bodies, but probably even on the other bodies it happened at some point. And so if we understand it better, it might illuminate some questions we have there. So I'm making a list of what I think good questions for our next workshop would be, and if you guys do that as well, maybe we can compare notes.
That's what I'm doing too, yeah.
Good, good. And for anybody listening in or participating online, we want this to be as inclusive as possible. So please don't feel like maybe if you weren't a speaker during this workshop that there's any reason that you shouldn't speak up. We want to hear from you, and we'd like to have you very much involved. So Amanda, are we ready to close it out for now? Let people go to lunch.
So. Should we break for lunch and come back in 1 hour, right?
Yeah.
So we'll start promptly in 1 hour. And so anybody who's dialing in can know we're going to get started in 1 hour.
Okay, so that's going to be 11:45 Pacific time, 12:45 Mountain, right?
Yeah.
Okay, very good. Thanks, everybody. It was a great start to our morning. Really appreciate it. And let's thank all the speakers again.